Here's a fraction. The numerator is simple, 15, but the denominator is not simple at all. Root 6 take away root 2. It has radicals in the denominator, and it in fact has two of them, separated by a subtraction symbol. I'm going to multiply this fraction by 1, but I'm not going to write 1. I'm going to write root 6 plus root 2 over itself. And I'll tell you why I'm doing that in a bit. First thing I'm going to do is put parentheses around our binomials for convenience. And then I can apply the rules for multiplication of fraction by writing it as like this. And now I'm going to do the multiplications. And at the top, it's the distributive property. And at the bottom, I'll take you through it step by step. I start with the root 6 on the far left, and I multiply it by the first root 6 in the second binomial. Well, root 6 times itself is 6. And then I take the root 6 times the second root 2 in the second binomial, and root 6 times root 2 is root 12. And now I go to the first binomial, and I have the negative root 2. Well, negative root 2 times root 6 is negative root 12. And my final product is negative root 2 times positive root 2, which is negative 2, because it makes negative root 4, and the square root of 4 is 2. And with the negative on the outside, that becomes negative 2. Or as we've written it, subtract 2. Well, the good news here is notice in the middle of the denominator we have root 12 take away root 12. Well, that makes 0. So now we need more room, but all that's left in the denominator now is 6 take away 2, which of course is 4. And in fact, you can stop here because 15 and 4 have nothing in common. But some people like to multiply the 15 through. So I'll take either one of those expressions in the circle as being a simpler form than our original problem. And that brings us to something called conjugates. For any two real numbers a and b, the binomial a plus b and the binomial a minus b are called conjugates. And then that leads us to the product of conjugate radical binomials. For any non-negative rational numbers x and y, the quantity of the square root of x plus the square root of y times the quantity the square root of x minus the square root of y is equal to x take away y, which is a rational number. So now we have a similar problem to our first one. So now we're looking for the conjugate, and our conjugate is root 6 minus root 2. So we do the work, and we didn't show it here, because in our first problem, our denominator was root 6 minus root 2, and we multiplied it by root 6 plus root 2. So we're doing the same thing to the denominator here. It's just that our binomials are in reverse order. But because of the commutative property, the answer is still going to be 4. And then, of course, you can multiply the 15 out, and I'll take the answer in either form. So the difference between the two problems was, in the first problem, it was 15 root 6 plus 15 root 2 over 4. And in our second problem that we're looking at now, the final answer is 15 root 6 take away 15 root 2 over 4. Here's one where our denominator has a radical in it, and it's a binomial, but the other part of the binomial is a rational number, 8. But the conjugate is root 6 take away 8. And now we do the multiplication, and of course root 6 times itself is 6. Root 6 times negative root 8 is negative 8 root 6, which I've written minus 8 root 6. The 8 times the second root 6 is 8 root 6, and the 8 times negative 8 is negative 64, which we've written minus 64. And once again, in the middle, we have a negative 8 root 6 and a positive 8 root 6, so they make 0. We go to a new page, and that leaves us with 6 take away 64, which is negative 58. And since 18 and negative 58 are both even numbers, we can simplify, and we get 9 times the quantity root 6 minus 8 over negative 29. And if we like, we can bring the negative up to the top. Either way is fine. Both of the expressions at the bottom will work for this problem. Here's 5 plus 3 root 2 over 2 take away 4 root 3. We find the conjugate for the denominator. which is 2 plus 4 root 3. Now we have quite a bit of multiplying to do, and I've done it. I didn't bother to put the parentheses around everything, but I need to do 5 times 2 to get 10, 5 times 4 root 3 to get 20 root 3, 3 root 2 times 2 to get 6 root 2, and 3 root 2 times 4 root 3 to get 12 root 6. So the numerator is quite cumbersome because we have a root 3, a root 2, and a root 6, no common terms. The denominator starts with 2 times 2, which is 4, 2 times 4 root 3, which is 8 root 3, negative 4 root 3 times 2, which is negative 8 root 3, and finally, negative 4 root 3 times positive 4 root 3, which equals negative 16 root 9. And we notice that the 8 root 3 minus 8 root 3 makes 0. So we can cross that out, and we'll go to a new page and notice that the minus 16 root 9 has a radical there, but the square root of 9 is 3, and 16 times 3 is 48. So when we go to a fresh page, we've replaced it with a 48. We have 4 minus 48, which of course is negative 44. And we also notice that our numerator can be factored. All of those terms could be divided by 2, so we did that and brought the 2 out, and now we can cancel the 2 and the negative 44 to get a negative 22 on the bottom, and then we'll go to one more clean page to write it up in final form. It's still a pretty complicated problem, but there's no radical in the denominator. And just for the record, I've rewritten the original problem and our simplified answer. Our answer isn't that much simpler than our original problem, but it does follow the rules where we've gotten rid of the radical in the denominator, also known as rationalizing the denominator. Once again, we define conjugates for any two real numbers a and b. The quantity a plus b and the quantity a minus b are called conjugates. And that leads us to the product of conjugate radical binomials for any non-negative rational numbers x and y. The quantity of square root of x plus the square root of y times the quantity of the square root of x minus the square root of y is equal to x minus y, which is a rational number.